What is faster than the speed of light? For centuries, humanity has accepted that nothing can go faster than this speed. However, a group of scientists has managed to manipulate and break the speed of light for the first time. Needless to say, this achievement has generated lots of questions, as people want to know how they achieved it and what it means for us. In this video, we bring you how scientists just manipulated and broke the speed of light for the first time in history, and other amazing discoveries in the universe. If you're a fan of Coldplay, you may know about their song titled Speed of Sound. Sound travels really fast, but something else travels even faster: light. Light covers 299,772,458 meters per second, a truly mind-boggling speed. It is so fast that many people do not even realize that light travels. Think of the last time you switched on a light bulb in a dark room. Light filled up the room immediately. However, when the sun produces light, it takes more than 8 minutes to reach the Earth, but that is because the sun is about 93 million miles away. The speed of light is an essential component of physics, but how did that come to be? The first genius to realize that light has a speed was an astronomer named Rømer. In the late 1600s, he was studying what appeared to be strange motions of the moon Io around Jupiter. He noticed that every once in a while the massive planet would block its little moon from our view from the Earth, which caused an eclipse. However, the timing between eclipses varied over the course of the year. After some years of observations, Rømer realized that when Io got eclipsed, the Earth was in a certain position in its own orbit around the Sun. But by the time the next eclipse came, the Earth would be in a slightly different position a few days later. He reasoned that if the Earth was further away than the last time an eclipse was observed, it meant observers had to wait a little bit of extra time to see the next one because it takes much longer for the light to reach them. The reverse was the case when the Earth was a little bit closer to Jupiter. Rømer concluded the only suitable explanation for the variations in the timing of eclipses of Io was if light had a finite speed. Of course, Rømer lacked the instrument necessary to accurately determine the speed of light. Scientists after him continued to take measurements until the mid-19th century, when a physicist named James Clerk Maxwell accidentally made an important discovery about the speed of light. Maxwell was working with electricity and magnetism when he realized that changing electric fields could create magnetic fields and vice versa. The physicist then calculated the speed of the electromagnetic waves and was shocked to discover it matched the speed of light scientists had been measuring. It showed clearly that light was made of electromagnetic waves, which determines its speed. However, another genius would arrive that would turn things upside down. That was Albert Einstein with his theory of relativity. The scientist showed that there was a single constant, or a certain speed, that could tell us how much space was equivalent to how much time and vice versa. And thanks to how vast the universe is, light from stars takes billions of years to reach us. We see the light from the closest star to us, Alpha Centauri, after it has traveled 4.35 years. Light from some stars has been traveling billions of years before they reach us. Now, if there is a certain speed at which light travels, can anything ever travel faster? Under Einstein's theory, the speed of light is a kind of ultimate universal speed limit. This means that objects possessing mass can't reach the speed of light because they would need infinite energy to do so. So your car or aircraft may never travel at the speed of light. However, a group of physicists has demonstrated that waves made up of groups of photons could travel more quickly than light. Researchers have been speeding up or slowing down light pulses for some time, using things like refractive crystals, optical fibers, and cold atomic gases. But what these scientists from Lawrence Livermore National Laboratory in California and the University of Rochester in New York have done is successfully adjust the speed of light waves within plasma. The fine-tuned waves range from about 1/10 of the usual vacuum speed of light to more than 30% faster. How did the scientists achieve this feat? It boils down to electromagnetism. This force, which is the interaction of electrical and magnetic fields, keeps a photon's speed constant. These low-frequency photon pulses bump against each other in ways that produce periodic waves. Then there is the group velocity, which may move more slowly or quickly depending on the electromagnetic characteristics of its surroundings. Actually, the group velocity is the rhythmic rise and fall of entire groups of light waves as they flow through matter. What these researchers did was use a laser to remove electrons from a stream of hydrogen and helium ions, and they were able to slow down or streamline the delivery of light pulses. This changed the group velocity of the light pulses sent through them and made the characteristics of the pulse change shape. Something else that came into play was refraction from the plasma fields and the polarized light from the main laser. Even when the collective dance seemed to quicken, the individual light waves moved at their usual speed. The experiment provides more information about the physics of plasmas. It also introduces new restrictions on the precision of current models based on theoretical points of view. Lawrence Livermore National Lab is home to some of the world's best laser technology. While being able to travel at the speed of light brings many benefits, including traveling to distant places in the universe, this achievement does not mean we are building spacecraft that can attain the speed of light yet. However, this experiment can help get humanity closer to the kind of future we dream of. Speaking of light traveling, the James Webb Space Telescope has captured light from an alien world for the first time, allowing it to take photos of the distant planet. Scientists had known that the JWST would be one powerful space telescope. It was built at the exorbitant cost of $10 billion and packed many sophisticated parts and mechanisms to allow it to look very far into space. However, it's still a surreal moment to see the Space Observatory return the photo of its first exoplanet. Exoplanets are notoriously hard to track or picture. These distant planets are a rather recent discovery, as it was within the last few decades that we knew planets could orbit stars, and our own solar system is not so unique. Scientists have discovered over 5,000 exoplanets, with the majority of them detected indirectly. They orbit so close to their host stars that with current technology, it is simply impossible to see them directly. Instead, astronomers watch out for their host stars doing something unexpected and infer from that the presence of exoplanets. Of all these exoplanets, only a handful have been seen directly. The most popular one discovered directly is HR 8799, whose 4 giant planets have been imaged so frequently that astronomers have produced a video showing them moving in their orbits around their host star. However, the JWST has changed the game. The telescope was used to capture the HIP 65426 star, which has a massive planet, the HIP 65426b, orbiting it. The exoplanet was discovered using the direct imaging method some years back. Exoplanet HIP 65426b is fascinating for many reasons, and some of these reasons make it a good candidate for detection using direct imaging. For example, the exoplanet is a long way from its host star. It orbits roughly 92 times further from HIP 65426 than the distance between Earth and the Sun. That's an orbit of about 14 billion kilometers from its star. From our vantage point, this makes for a nice distance from the star in the sky, making it easier to sight. Also, HIP 65426b is a behemoth of a planet. It is estimated to be several times the mass of our solar system's biggest planet, Jupiter. On top of that, it was reported to be one hot planet, with the temperature at its cloud tops measuring at least 1200 degrees Celsius. This combination of the planet's size and temperature means it's very bright as planets go. However, even at the wide orbit from its parent star, the light from HIP 65426 would utterly overwhelm that from HIP 65426b. But the JWST gets around this problem. The JWST has some coronagraphs or instruments that help the telescope block the light from a bright star to look for fainter objects beside it. Think of when you block the headlights of a car with your hand to see whether your friend has climbed out. Using these coronagraphs, JWST took a series of images of HIP 65426b. Each image was taken at different wavelengths of infrared light. In each image, the planet can be clearly seen. It is a single bright pixel offset from the location of its obscured stellar host. Of course, the images are not the high-resolution images found in fiction movies, but they show that the planet was easily detected, standing out against the dark background of space. The researchers who led the observations admitted they gained a new respect for the JWST. The telescope is performing around 10 times better than expected. Using the observations, the researchers were able to determine the mass of HIP 65426b. Beyond that, the data reveal that the planet is hotter than previously thought. The cloud tops are close to 1400 degrees Celsius. They also discovered that it was slightly not as big as thought, with a diameter about 92% that of Jupiter. These images paint a picture of an utterly alien world, different from anything in the solar system. Apart from yielding images of an exoplanet, this observation is proof of what the JWST is capable of when it comes to exoplanets. It suggests the Space Telescope will be able to obtain direct observations of planets smaller than previously expected. Rather than being limited to planets more massive than Jupiter, it should be able to see planets comparable to or even smaller than Saturn. Scientists are excited because the JWST, being able to see smaller and fainter planets than expected, means the number of possible targets available for astronomers to study will greatly increase. Besides that, the precision with which the JWST made these measurements shows we'll be able to learn far more about their atmospheres than expected. In fact, repeating observations with the telescope could reveal details of how these atmospheres vary with time. Let's hear what you think of the wonders of the universe in the comments section below.